Verifying simple differential identities. Hello, everyone. Let's begin our lesson on verifying simple differential identities. To start, let's look back at what we have already covered. In our previous subsections, we spent time mastering the process of computing both the first and second-order derivatives of a function. Now, we are going to move forward and apply those specific skills to a new task, verifying differential identities. You might be wondering what a differential identity is. In simple terms, a differential identity, which you may also hear referred to as a simple differential equation, is an equation that involves both a function and its derivatives. When we are asked to verify such an identity, we aren't solving for an unknown variable. Instead, our goal is to prove that a specific function provided to us actually satisfies the given equation. Essentially, what we are doing is checking to see if the mathematical relationship between the function and its rates of change holds true. In the next few slides, I will walk you through the systematic process of how to perform this verification and show you how these identities are used in real-world physics. The step-by-step process of verification. Now that we have established what a differential identity is, let us move on to the systematic process we use to verify one. To prove that a function, y equals f of x, satisfies a given differential identity, you should follow these four structured steps. First, you must find the first derivative. This involves differentiating the given function y with respect to x to determine the value of di by dx. Second, you will find the second derivative. To do this, simply take the result from the first step and differentiate it once more with respect to x to find d squared y by dx squared. The third step is substitution. At this stage, you will take your expressions for y, di by dx, and d squared y by dx squared and substitute them into the provided differential equation. Finally, we perform simplification. By using algebraic or trigonometric identities, you will simplify the resulting expression. If the left-hand side equals the right-hand side, the identity is officially verified. Once you are comfortable with this step-by-step workflow, we will see how this mathematical process is used in physics to describe real-world motion in our next slide. Real-world application, simple harmonic motion. Now that we have established the theoretical framework and the step-by-step process for verification, let us take a moment to understand the practical significance of these concepts before we move into the calculations. In the field of physics, the repetitive back-and-forth movement of a weight hanging from a spring, or the steady swing of a pendulum, is known as simple harmonic motion. In such a system, the acceleration of the object, which, as we have already discussed, is represented by the second derivative of the position, y with respect to time, x, is proportional to the displacement of the object, but it acts in the opposite direction. Mathematically, this physical relationship is expressed through a differential identity. The second derivative of y with respect to x plus k times y equals 0, where k is a constant. By verifying these types of identities, scientists are able to create accurate models to predict the exact position of an object at any given point in time. With this real-world context in mind, let us now proceed to the next slide, where we will apply our verification steps to a detailed mathematical example. Detailed example. Now that we have discussed the theoretical process and seen how these identities apply to real-world physics, let us put everything into practice with a detailed example. Please look at the problem on the screen. We are given the function y equals a sine x plus b cosine x, where a and b are constants. Our goal is to prove that this function satisfies the differential identity, the second derivative of y with respect to x plus y equals 0. To do this, we will follow the systematic four-step process we outlined in the previous slide. Starting with step 1, we need to calculate the first derivative of y with respect to x. We begin by differentiating the entire expression. The derivative of a sine x plus the derivative of b cosine x, since a and b are constants, they remain unchanged during differentiation. Recalling our trigonometric rules, the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. Therefore, the first derivative of y with respect to x is a cosine x minus b sine x. Moving to step 2, we find the second derivative. This simply means we differentiate our previous result with respect to x once more. We take the derivative of a cosine x minus b sine x again. Applying our rules, the derivative of cosine x becomes negative sine x, and the derivative of negative sine x becomes negative cosine x. This gives us a second derivative of negative a sine x minus b cosine x. Now we proceed to step 3, substitution. We take the identity we are verifying, which is the second derivative of y with respect to x plus y equals 0. We will focus on the left-hand side of the equation. By substituting the expression we just found for the second derivative and the original expression for y, the left-hand side becomes negative a sine x minus b cosine x plus a sine x plus b cosine x. Finally, in step 4, we simplify the expression to verify the identity. If we group the like terms, we see that negative a sine x cancels out with positive a sine x, and negative b cosine x cancels out with positive b cosine x. This leaves us with 0 plus 0, which equals 0. Since the left-hand side equals the right-hand side, we have successfully verified that the identity, the second derivative of y with respect to x plus y equals 0, holds true for this function. As we move to the next slide, I want you to keep a close eye on the signs we use during these steps, as this is where most students encounter difficulties. Common mistakes to avoid. Now that we have walked through the detailed example, let us discuss some common pitfalls to ensure you avoid them in your own work. First, be very mindful of sign errors in trigonometry. A very frequent mistake is forgetting that the derivative of cosine x is negative sine x, and the derivative of sine x is cosine x. I strongly advise you to double-check your signs, particularly during the second differentiation step, as a single missed minus sign will prevent the identity from being verified. Secondly, be careful not to confuse constants with variables. If you recall the example we just solved, the letters a and b were constants. Remember that we do not take the derivative of these constants. We only differentiate the functions, such as sine x and cosine x, that they are multiplying. Finally, avoid incorrect substitution. When you reach the substitution step of the process, ensure that you substitute the entire expression for y and the second derivative of y with respect to x into the equation. Do not substitute only parts of the expression, as the identity requires the full function to be present to hold true. By keeping these points in mind, you will significantly reduce errors in your calculations. Now, let us move on to the final slide to summarize the key takeaways from this lesson. Key takeaways. To wrap up our lesson, let's review the key takeaways from this section to ensure you have a solid grasp of the concept. First, remember that verification is simply the process of proving that a specific given function satisfies a differential equation, effectively showing that the function makes the equation true. As we demonstrated in our detailed example, the process follows a very linear and systematic path. You begin with the original function, calculate the first derivative, then find the second derivative, substitute these expressions into the identity, and finally simplify the results to verify the equality. It is also important to keep in mind the practical side of this topic. These differential identities are fundamental tools in physics and engineering, particularly when describing oscillatory systems, such as the swinging of a pendulum or the motion of a spring, which we discussed in the context of simple harmonic motion. Lastly, as a final reminder based on the common mistakes we just covered, always maintain strict attention to your signs. When you are differentiating trigonometric functions multiple times, a single missed negative sign can change your entire result, so be sure to double-check your work at every stage of the process.